All right, good afternoon, everybody. I'm Tharanga Jayarathne with TRC, and today I'm going to talk about a project that we are conducting with the Center for the Built Environment and TEL engineers. In this project, we are focusing on optimizing HVAC performance in commercial buildings through what we call CORE. So CORE stands for Cost Optimized Reset. And I'll walk through what CORE means and results from a field demonstration study, as well as where we think this is going. So HVAC systems in commercial buildings are a major energy use. No need to mention that. There are multi-zone variable air volume systems or VAV systems that are widely used, but often found to be underperforming. One key lever to optimize these systems is the supplier temperature reset method. And there are existing reset methods like fixed outside air set point, fixed supplier temperature set point, or outside air temperature based set point, which have limitations that can lead to energy wasting or comfort issues. So these existing systems are suboptimal, which means there's a big opportunity for us to improve energy and cost efficiency of these systems. So what is CORE and how does it work? Just to give a little bit of a history, CORE was developed by the team at CBE, led by Dr. Paul Raftery. I don't know, at this point, maybe 7 or 8 years ago, maybe even before that. They've done work on it since then to improve the original algorithm. In fact, at last year's October meeting, Dr. Yan Wang from the CBE presented on a detailed energy modeling study that looked at the performance of CORE against existing strategies. So this field demonstration part is the next step of that project. So how does CORE differ from other strategies? Unlike traditional strategies, CORE dynamically resets the supply temperature set point based on HVAC cost. So it first looks at if the building requires cooling for comfort, that's that blue box up there. And if it requires cooling, it does go like vertically down, delivers cooling as necessary to meet the comfort requirements. And when the comfort is met, it then switches to the green branch, which is where CORE kicks in. So under CORE, it looks at the current supply air temperature set point and maybe a couple more candidate set points, and then calculate the energy cost. This includes heating, cooling, and fan energy cost for each of those set points. And then depending on what those costs are, it then picks the lowest cost supply temperature set point. And by doing this iteratively, it can optimize for the HVAC cost. So the good thing about this is that this is designed to be simple and can be implemented in existing building automation systems. We've also developed a simplified algorithm for the initial CORE algorithm, which needs less sensor data. So it's easier to program and easier to implement. So CORE overall is smarter than traditional reset methods because it actively optimizes for cost rather than relying on rules of thumb. So in this project, our goal was to refine CORE and implement it in real buildings. We wanted to see the impact on energy and cost from CORE as against existing strategies. And we also wanted to understand how we can scale this technology and also understand the barriers to implement it. So we went ahead and implemented this in 4 buildings. One of them is ongoing. And we evaluated energy and cost impact through measurement and verification techniques. And this whole work is funded by Southern California Edison through their CalNex program, NYSERDA, and the Center for the Built Environment. So as I mentioned, we implemented CORE in 4 buildings. 3 of them are in California. All 3 are medical office buildings. A 4th building is in New York, which is currently ongoing. For the California buildings, we partnered with a controls contractor who implemented CORE in a supervisory control layer in these buildings. So I just want to briefly show the process that we used to implement these, just to show you the scale that we were able to achieve as we went along. So in the first building, we have the supervisory layer and the controls contractor programmed core in that supervisory layer. Then mapped inputs and outputs to the building automation system, so that core could run in the supervisory layer but controls the building. And this whole process, including the initial programming, debugging, commissioning, took, there was months worth of work. But then they had a framework and a program that they can use easily in the next implementation. So for the next building, again, there's a supervisory layer, but they were able to use the same program with minor adjustments, and they then needed to map IOs to the second building's PAs, and this was much faster. It took them weeks to do it. And moving on to the third building, they just repeat the same process. Now they've learned from the first two buildings, and this one, it just took them a couple of hours. So this really shows like how fast we can do and the scalability of this method that we used in supervisory layers to implement core or any advanced control strategies in a portfolio of buildings. Now, after we implemented core in all three of these buildings, we then want to see how they perform against the existing strategies. So we sort of randomly switched between existing strategy as the baseline and core technology daily. By doing this, we were able to collect data sort of under similar external conditions, similar building conditions at the same time for both strategies. And I also briefly want to touch on a few details on the demonstration size, just to show you the scale of what we did. These three buildings range from 33,000 to 50,000 square feet in area, but the HVAC configurations were really diverse. They had rooftop units or AHUs, and in terms of heating and cooling, they had DX cooling or chiller plants, hot water boiler plants to generate hot water for reheat. We even had an all-electric building that's at the first building. So the key point here is that core was able to work well in all of these diverse conditions and really talks to the versatility of the technology. All right, let's talk results. So in summary, core was able to save both HVAC energy and cost in all three of these buildings. And in terms of the energy, it saved between 2 and 22%, depending on the condition and building status. And this was achieved through savings from heating, cooling, and fan energy. And this is also not like modeled energy. So this is real building savings that we measured. So that's the important thing. In terms of cost, core saved between 10 and 20%. Of course, the dollar value depends on the utility rates. For an example, in California, this optimization is more valuable. And this really speaks into the fact that core is a cost optimizing technology, not only an energy saving method. So the Wu-Tang Clan will be happy, I guess. I mean, these implementations, again, were not without challenges. We found a couple of barriers and learned from these. Algorithm complexity was one of them. So the controls contractors are used to implementing simpler strategies, simpler sequences. So core was a little bit of more work, which meant that having good documentation or support is important. And we found that existing conditions in the system, in the building, like HVAC system issues or limitations in the BAs, can be really challenging in some demonstration sites. But we also learned that this can be an opportunity to save energy, and using things like simplified algorithms or providing these advanced algorithms through programming libraries can really speed the adoption. And very importantly, a thorough evaluation of the existing systems and performing existing building commissioning is critical, not only for core to work correctly, but also because itself, this existing building commissioning can save a lot of energy. So with all this experience, we have two key recommendations here. One is we recommend packaging core into programming libraries offered by manufacturers. This reduces the burden for programming, and it's then easier to adopt into the industry. And we recommend pairing core with commissioning or retro-commissioning work and controlled retrofits. So the next steps for us is we will be continuing data collection at the New York demonstration site, and we'll look at the impact on energy and energy cost. We are going to present core to the industry as well as the ASHRAE Guideline 36 committee, which looks at optimized control sequences. This is going to help broader adoption. And then we've submitted a research paper for the ASHRAE Winter Conference that's coming up in January. And we are also currently distributing the CalNext project final report. So to wrap up, core demonstrated that it can save both energy and energy cost. It's a scalable and cost-effective strategy that can improve HVAC performance, but it's better when it's paired with existing building commissioning or retro-commissioning work. So core is now a field-tested technology that can save energy, reduce operational costs, and reduce greenhouse gas emissions. So with that, I'll stop. Thank you for listening. I can take any questions.